Hello class 11. The topic that we are going to discuss today is, as you can see written on the board, it's uniform circular motion. Now first let us focus on the last two words, circular and motion. So here therefore we are going to deal with a body moving in a circular path, and the motion has to be uniform. Uniform meaning the body is moving with a constant speed around that circular path, remember. So, though the body is moving with a constant speed, like you've already studied in class 9 and also in class 10, this kind of a motion, that is uniform circular motion, is a case of non-uniform velocity or non-uniform motion, and thereby it's a case of acceleration. So, the famous question that you dealt with in class 9, also in class 10, a body is moving with a uniform speed in a circular path. Is it a case of acceleration? And the answer, of course, was yes. Okay. So, first of all, let us try drawing a circular path. Okay, just a sec. Okay, so let's suppose that this is our circular path around which a body moves with a uniform speed. Say this is the center O, let's call it O, and initially let us suppose that the body is at point A. Now in time delta t, in a certain time delta t, what happens is the body moves from point A and reaches point B. So AB, so to say, is the linear displacement of the body. But here, of course, considering motion in a circular path, okay, what is of more importance to us rather than the linear displacement is the angular displacement of the body. And the angular displacement is delta theta. So, delta theta is the angular displacement the particle describes in time delta t when it moves from A to B, remember. So delta theta, as I've already mentioned, is called angular displacement. It's called angular displacement, remember. So like we have linear displacement or simply displacement in case of linear motion, displacement or distance, here we will have angular displacement. Now the unit to measure angular displacement, unit for delta theta or simply for theta also, in some books you will simply see the angular displacement represented by a theta. So the unit for angular displacement is radian. Okay, now remember, radian itself is a dimensionless quantity. Now, therefore, if you are to find the dimension of angular displacement, there is no dimension for angular displacement, or so to say, dimension for delta theta is m to the power 0, L to the power 0, t to the power 0 inside square bracket, of course. So this is the dimension of your angular displacement, remember. And by the way, angular displacement is a vector. Like linear displacement is a vector quantity, angular displacement also is a vector quantity, remember. The direction of angular displacement will be perpendicular to the plane in which the circular motion is being executed. So to say, since we are considering the movement of the body in this direction from A to B, that is, the body is going round about the circular path in anti-clockwise sense, in anti-clockwise direction. So therefore, the direction of our angular displacement will of course be perpendicular to this plane of the board, so to say, the plane in which the motion is being executed. Now, perpendicular to the board, it could be going into the plane of the board or coming out of the plane of the board. So, which perpendicular direction will that be? Now, that is given by the right hand thumb rule. The four fingers curls in the direction of motion of the body, alright, and the thumb gives you the direction of the angular displacement. So in this case, since the motion of the body is being executed in the anti-clockwise sense, so therefore our forefinger curls in that direction and the thumb gives us the direction of the angular displacement, so to say. Okay, thumb of your right hand, remember, right hand thumb rule. So to say, in this case, the direction of the angular displacement is perpendicular to the plane of the board, or more precisely, coming out of the plane of the board perpendicularly. So this is the direction of your angular displacement, remember. And don't forget, angular displacement therefore is a vector quantity. It has a certain magnitude and it has a direction. So this is about our angular displacement. Now, we've studied about, or we've learned about linear velocity when we are talking about motion of a body in a straight line. Okay, velocity was the rate of change of displacement. Likewise, when a body is moving in a circular path, since we have angular displacement, we also talk about omega. Okay, the small letter Greek letter. So this is not W, remember, this is omega. The capital letter omega you're already familiar with. This is the capital letter omega, denoting, you've come across this while studying resistance. Okay, the unit of resistance, ohm, so to say. So this is the small letter omega. So omega denotes your angular velocity. Okay, and how is omega defined? Omega is defined to be the rate of change of angular displacement. So to say, delta theta divided by delta t. So this is your angular displacement, remember that. If delta t is very small, such that delta t tends towards 0, then omega can also be written as dw, oh, sorry, I myself am saying dw, it's not dw, it's d omega. So d omega by dt. So omega is also defined this way, remember. Sorry, your angular displacement, if t is very small, then omega is d theta divided by dt. This is your definition for angular velocity. Either this or this. Delta represents the change. Now if the change is very small, if the time is very small, the change would be small, okay? So therefore small change is represented by d theta, or small change in time by dt, remember that. So this is your definition for angular velocity. Since angular displacement is a vector quantity, likewise the angular velocity is also a vector quantity. The direction of angular velocity is the same as that of your angular displacement, which is perpendicular to the plane of the board, or perpendicular to the plane in which the circular motion is being executed, and it of course is given by your right hand thumb rule, remember that. So to say, the direction of omega is also coming perpendicularly out of the plane of the board. So this is about your angular displacement and angular velocity. There are, oh, by the way, here, what is unit of omega? Unit of omega, it is the SI unit, so to say, is radian per second. Radian per second, also denoted by RAD per second, and this is the SI unit, remember. Likewise, radian is the SI unit for angular displacement. I forgot to mention that earlier. So this is your unit for angular velocity, the SI unit. You can of course use another unit also, which is degrees per second. But generally, since this is the SI unit, we use this radian per second as the unit of angular velocity. Alright, so let me erase this part. You can pause the video and copy. I hope you've done that. So, what is the dimension of omega, by the way? The dimension of angular velocity. The dimension of angular velocity will be m to the power 0, L to the power 0, t to the power minus 1, remember, because radian is dimensionless, so per second gives you t to the power minus 1. Okay, this will be the dimension of angular velocity, don't forget that. Okay, now relation between linear velocity and angular velocity Sometimes you get a 2 marks question asking you to derive the relation between linear velocity and angular velocity. Linear velocity is v, small v, okay, and angular velocity is your omega, don't forget. Now, you must have studied, while, I don't know whether you studied circles in class 10 or not, but there's one relation which says that the angle described at the center, this is the angle described at the center, of course. In our case, it is delta theta. The angle described at the center is equal to arc divided by the radius. Okay, so you can start with we know delta theta is equal to arc by radius. Now, what is the arc? Arc is AB over here. Okay, divided by the radius. In this circular path, the radius throughout is constant, of course. If, say, radius is r, then here I can write or delta theta is equal to AB divided by r, so to say. Now, dividing both the sides by delta t, I can write delta theta by delta t is equal to AB by delta t into 1 by r. Now, mind you, this is not the dot from the dot product, remember. This is simply mathematical multiplication sign, so to say, dot for that. Okay, it is not from the dot product, remember. Okay, now see, if delta theta is very small, if your delta t is very small, then of course delta theta will be small. Okay, so if delta t tends to 0, without assuming this also, you can see that the left hand side is your omega, angular velocity. This is equal to AB upon delta t. AB is the displacement over here, and if delta t is very small, what happens? AB will be a straight line. If B is somewhere very close over here. If delta t is very small, the angular displacement delta theta will be very small. So B is somewhere over here. Okay, so this distance you can consider it to be a straight line, of course. So AB divided by delta t is what? It is displacement divided by time. This is a linear velocity, mind you. So linear velocity into 1 upon r, so to say. So if delta t tends to 0, we can rewrite this equation as d theta divided by dt is equal to AB by dt, that small change in time, into 1 by r. Okay, so I'm erasing this part now. So from there, therefore, I can write d theta divided by dt is what? It is our omega. So this is equal to AB upon dt is your linear velocity divided by your radius, so to say. Or thereby we get V is equal to omega into r. So this is the relation between your linear velocity and your angular velocity. Now, if you want to write this relation vectorially in vector form, so to say, then this can be written as V is equal to our vector, the linear velocity vector is equal to omega, which is a vector itself, cross r. It's a cross product, so to say. Okay, why? Because omega is in this direction, coming out of the plane of the board. Okay, r, if you consider it to be a vector, since it's displacement basically, radius is displacement. So we have two vectors, one in this direction and the other is in this direction. Now, to find the direction of V, what we do is we use a right-handed screw. You have to go back to your cross product thing, okay, because the cross product of two vectors gives us a vector whose direction is given by right-handed screw, and we rotate our right-handed screw from the first vector here, omega, to r. So from omega to r, I rotate my right-handed screw. My right-handed screw moves in the upward direction. Okay, so to say, the direction of V is in this direction. Alright, the direction of V is in this direction, perpendicular to both the direction of omega and that of r, as you can see. Alright, and do remember, the direction of velocity, so to say, is always along the tangent to the point where we are calculating the velocity. If we are calculating the velocity at this point, the direction of the velocity is always along the tangent to that particular point. So this is the direction of velocity, remember. If you calculate velocity over here, it is along the tangent to that particular point. Okay, and don't forget, the angle between the tangent and the radius is always 90 degrees. You've learned this in mathematics also. So this angle is 90 degrees, this angle is 90 degrees. At any point you draw the radius and the tangent, the angle is 90 degrees. Remember that. Alright, so this is the relation, vector relation between linear velocity and angular velocity. Okay, now if from here itself we can write, since the cross product is V is omega r into sine theta, right? Theta is the angle between these two vectors. But the angle between omega and r, as you can see, is 90 degrees. So this theta is 90 degrees. Now what is sine of 90 degrees? Sine of 90 degrees is 1. So therefore we get this omega r. So from this relation we are getting this. Are you understanding? Okay, so V is omega r is, so to say, the scalar form or scalar relation between velocity and omega, your angular velocity. So this is about the introduction to uniform circular motion. In the next video, we'll of course further talk about uniform circular motion. In the next video, we are going to talk about centripetal force, and we are going to derive the relation for centripetal force. Because do remember, centripetal force means center seeking force. Okay, let me not do the explanation for centripetal force in this video. We'll keep that for the next video. So do remember, centripetal means center seeking force. That is, the force is always directed towards the center at any point. If we measure the force at this point, the direction is towards the center. If we measure the force at this point, the direction is towards the center. At this point we measure, the direction is towards the center. So at any point, the direction of the centripetal force is always towards the center. Therefore, we call it center seeking force, and that is exactly what we are going to discuss about in the next video. And we also are going to derive a relation for it. Alright? Thank you for now.